Hey guys, welcome back to chapter 11. We are going to introduce our last of the colligative properties, and that has to do with osmosis or osmotic pressure. Osmosis is defined as the flow of a solvent. Okay, so big word, keyword here, solvent is moving. So what is our solvent most of the time? It's water, right? So we're talking about the flow of water from one place to another. Okay, so the solvent will flow from a solution of low concentration to a solution of high concentration, so low to high. What allows the solvent to move but not the solute? Something called a semi-permeable membrane. Okay. So the semi-permeable membrane will allow the solvent to flow, but it holds the solutes in place. The most popular semi-permeable membrane in biologic systems is the cell wall, right? So we can have water flowing into and out of the cell, but all of the contents of the cell stay in the cell, and all the contents on the outside of the cell stay on the outside of the cell. And if we need to exchange contents, there's a much more complex system for that. So big thing here is solvent moves, and it moves from low to high. So here's just a picture of a solvent moving. So here in the first one, we see the solvent, the water lines are the same. The yellow represents water molecules. The purple represents a solute particle. So at time equals 0 at the beginning here, we see the levels of water are the same. Now, if we open up a valve, allow that solvent to flow, what we are going to see is the solvent will flow from low concentration over here where it's pure into the solution of high concentration. So it'll go here from left to right. And that's exactly what we see in the second snapshot. The water level in the right side is much higher than the water level in the left side. The movement of that solvent, the movement of the water, is due to that difference in osmotic pressure. So this is where we see that change. So what has been the theme of this chapter? It's been colligative properties. It doesn't matter what the solute is. What matters is how much is in that solution. Okay. So what we're going to calculate here is this osmotic pressure, the pressure exerted by the solution to kind of stop that flow of solvent. So the solvent will flow until the pressure gets so high, then it says stop, and it stops that flow. So here's our formula for osmotic pressure. Osmotic pressure is denoted with this kind of pi symbol here, and it's a collection of 3 different variables. So the first variable is molarity. So one thing to note here, that's that capital M. We're talking about moles per liter. And this is, again, how we address how many particles are there, right? So molarity. Then we've got the ideal gas constant. So when we're talking about the pressure, ideal gas constant comes into play. That is a constant. It's always 0.8206. The units on this, remember from the gas law chapter, really funky, cumbersome units. But it's ATM liters divided by moles Kelvin. That is not a formula. That is the unit. But again, we're going to see that is awfully handy when we start mathing. The temperature of the solution matters. So the temperature has to be in Kelvin. So this is just part of that ideal gas constant. We saw it back in the gas law chapter. That those units have to match, so the temperature has to be in Kelvin. All right, so let's dive into an example. This is about as hard as I can make an example. We've got to determine all of the variables. So if we can get through this example together, I think you can tackle anything that might appear on the test. So here's our example of osmotic pressure. Calculate the osmotic pressure of a solution containing 1.5 grams of ethylene glycol in 50 grams of solution at 25 degrees Celsius. So over here, I'm just going to quickly take inventory of what I know, trying to figure out what I'm solving for, and then fixing any variables that need to be fixed. So osmotic pressure, molarity, ideal gas constant, and temperature. So reading back through the problem, calculate the osmotic pressure. We are solving for this value right here. In a solution containing 0.5 grams of ethylene glycol in 50 mils of solution, that's the information we need to calculate molarity. So remember, molarity is moles per liter, so moles of solvent per liter of solution. So we need to determine the number of moles of ethylene glycol looking at a periodic table now to determine the molar mass of ethylene glycol. I've got carbon 12.011 times 2 plus hydrogen, which is 1.008 times 6 plus oxygen, which is 15.999 times 2. Oh, that's not right. Now we get the molar mass of ethylene glycol is 62.07. Multiply across the top, divide by the bottom, so 1.50 times 1 divided by 62.07, and I get the moles as 0.0241. So that's the value that goes on the top of this equation. On the bottom is our liters of solution. Of course, the solution's given to us in milliliters. So just a quick conversion from milliliters to liters. So 50 milliliters, liters on top, milliliters on the bottom, and 1 liter. There's 1,000 milliliters, so we're dividing by 1,000. Again, if you can do this in your head without writing it out, that's fine. We get 0.05. So plug that in, 0.0241 divided by 0.05, and we get the molarity is 0.482. And actually, I'm going to take this molarity, I'm going to make it moles over liters, and that's going to help us later. All right, the ideal gas constant is just as it states. It is a constant, so it is the 0.08206. And then the crazy units of ATM liter over mole Kelvin. The last variable I need to fill in here is our temperature. Of course, they give us 25 degrees Celsius, but I cannot use Celsius in my equation. I have to transfer that to Kelvin. This conversion, again, will be given to you on the exam, but it is 273 plus temperature Celsius, So our temperature in Kelvin is 298. So that goes here. Now we have all of our variables in the correct format. We are ready to plug and chug. Plug it into our equation and chug our way through it. So the osmotic pressure equals molarity, which is 0.482, times the ideal gas constant, times the temperature in Kelvin. All right, here's where our wonky units pays off. So looking at my units in this problem, I see Kelvin on the bottom and I see Kelvin on the top. Those cancel. I see liters on the bottom. I see liters on the top. Those cancel. And I see moles on top, moles on the bottom. Those cancel. The only unit that's left is ATM. And we're solving for a pressure. So having the unit ATM for our pressure makes a whole lot of sense. So I'm going to plug this into my calculator. I get 0.0482 times 0.08206 times 298. And the osmotic pressure for this solution is 1.18 ATM. So pretty straightforward calculation on the osmotic pressure. In the last slide for this, the last lecture for this chapter, we're going to talk a little bit more about osmotic pressure and some applications of it, some definitions of it in kind of real world examples. I hope you guys found this helpful.